Hello E11s, welcome back. We are moving on to solar systems and circular orbits from P8.3. Okay, so in this lesson, what we are going to see is we are going to see the main parts of solar system, what all belongs to the solar system, and the different types of orbits and how do they manage to keep that in the circular or how do they manage to keep the objects in the circular orbit itself. Okay, so let's start. So we're going to start with, as I said in the previous slide, what is in our solar system? What are the main parts of our solar system? So definitely our sun, the star, which is at the center of our solar system. Then we have planets. These planets are spherical objects that are orbiting around the sun. We have 8 planets at the moment in our solar system, and we have divided them into 2 categories. One, inner planets. So that is the Mercury, Venus, Earth, and Mars. These are our inner planets. These planets are quite rocky and they have an atmosphere also. So these 4 are our inner planets. Now we are moving on to our outer planets, which is Jupiter, Saturn, Uranus, and Neptune. In this, Jupiter and Saturn, they are known as gas giants, and Uranus and Neptune, they are known as ice giants. Okay, so we have the sun in our solar system, we have the planets in our solar system. What else? We have moons in our solar system. So these planets are actually revolving around the sun, isn't it? We have something else that revolves around the planets, and that is the moon. Okay, so moon are objects in orbits that revolve around the planets. So we have a natural Earth's moon is called as moon itself, isn't it? That is our natural sort of satellite. Like that, the other planets also have moons, and if you go to the outer planets, they have loads and loads of moons. Then we have something called minor planets. Okay, so these minor planets are basically asteroids and other dwarf planets like Pluto. Now, what are these asteroids? They are pieces of rock that has been left over from the formation of a solar system. Okay, minor planets are not actually planets, nor do they come under the category of comets, which we will see next. And then we have the comets. They are made of ice and dust, and they orbit around the sun. So these are the main parts of our solar system: the sun, the planets, the moons, the minor planets, and the comets. Is that okay, all of you? Shall we move on? Next, we are moving on to natural and artificial satellites. So satellites is a word that should be really very common to you. So there are 2 types of satellites. One is the natural satellite and the other is the artificial satellites. So what are these satellites actually? Satellites are just planets. Satellites are just objects that revolve around a planet. Okay, and just in the previous slide we said moons are the objects that revolve around a planet, isn't it? Which means moon is also a satellite. Moon can be called as a satellite. So there are 2 types of satellites. One, the natural satellite, and the other, the artificial satellite. So just as I said now, moons are the best example for natural satellites. So they are revolving around the planets in the solar system. Now they are made of the same material as the rest of the planet. And then how do they move around the planet? Which type of orbit do they take? What is the shape of their orbits? All those things. They are generally moving in circular orbits. Now, how do they move around in those circular orbits? The position of those orbits, all those things, they can be very different from those of artificial satellites. So regarding natural satellites, all you need to know from the exam point of view is they are objects that are revolving around the planets, and they are made of the same material as the rest of the solar system. Now, how they are moving around the planets, we will come back to that once we do artificial satellites. So the natural satellites are already present in the solar system. We didn't do anything there. But when we come to artificial satellites, Those are the man-made objects that have been sent from Earth using rockets to orbit the sun and other planets. Earth already has more than thousands of artificial satellites around it. Now, when we come to artificial satellites, they have two specific paths that they take. Either they will be in the geostationary path or they will be in the polar path. Now, what does all those things mean? I'll tell you in the next slide. So in the previous slide, when we talked about artificial satellites, we said they will either follow a geostationary path or a polar path. Now, what does that mean? That is what we are going to see in the next two slides. So for all the artificial satellites that we have sent to orbit around the Earth, they have to follow one of the two orbits that we are going to discuss. So the first one is called the geostationary orbit. Geostationary means it looks like it is stationary. Now, why does it look like it is stationary? Because now, geostationary orbit means it is an orbit that as you can see in the picture here, it is an orbit that is going around the equator. Okay, can you see it is in that plane here? It's going like this. So it is a circular orbit. It is above the Earth's equator and it is roughly at this particular height, 36,000 kilometers. It is around 35,800, that range, but we can, at the moment, we can approximate it to 36,000 kilometer. Now, there is a reason why it has to be at that particular height itself. So geostationary orbit is a circular orbit that is above the Earth's equator at a height of 36,000 kilometers. Now, the time period, that means the time the satellite takes to go around the Earth. So the time period for one such orbit, for such satellites, for one orbit is 24 hours. Now, what is the significance there for 24 hours is it is the same as the time period of the Earth. So the time the Earth takes to go around the sun once is 24 hours. And the time these geostationary satellites are the ones that are going in these geostationary orbits. So these geostationary satellites will take the same time as the Earth takes to move around the sun. Now, what is the advantage of that? Say, think about you, your friend and you. You both are walking at the same speed in the same direction. Okay, so every time you look towards your right, say, what your friend will be there. You look after 5 minutes, your friend will be there. You look after 10 minutes, your friend will be there. Why? Because both of you are moving at the same speed in the same direction. That is exactly the thing that is happening here also. It is moving at a speed of 24 hours, which is the same as that of the Earth, and it is moving in the same direction as the Earth moves. Now, why are we doing this? We are doing this because we know then exactly where the satellite is. So when you're walking with your friend at the same speed, same direction, you know exactly where to look for your friend. So somebody asks you, where is he or she? You can just look to your right and say, there she is. But if you don't know the speed at which your friend was moving, if you don't know the direction at which your friend was, if you don't know the direction in which your friend was moving, then it's difficult for you to find out where your friend is. So, because they are moving at the same speed and in the same direction as the Earth, they remain fixed, or it looks like they are in a fixed position above the Earth. And because of that, they can be used for communication and satellite television. Why is that important? Because I have to communicate. For me to make my communication easier, it is better if I know where the person is, isn't it? I know where to find the person, then immediately I can go there and tell the person, see, this is what has happened. But if I don't know where the person is, I go to A first asking, oh, where is the person? Then A tells me, saw the person somewhere. I go there. They tell me, no, they moved to somewhere else. So it's going to take me ages and I'm going to go just beating around the bush like that without finding actually where the person is. So the advantage of geostationary satellites are, since they are moving at the same speed and the same direction as the Earth, they remain fixed at a position. It looks like they are remaining fixed at a position. So for communication, when we have to send signals from the Earth, we know exactly where to send it. And when we have to receive signals, we know exactly from where to receive it. Okay. And that is the reason why we are using geostationary satellites for communication and satellite television. Okay. So geostationary orbit is a circular orbit which is above the Earth's equator and it is at a height of 36,000 kilometers. The speciality of geostationary satellites are that their time period is 24 hours, exactly like the Earth, and they move in the same direction as the Earth. So what is the advantage of these two things? Because of these two things, it looks like the satellite is fixed at a position. So we can easily send signals, we can easily receive signals. Okay, and because of that, they are used for communication and satellite purpose. Is that clear, all of you? Is geostationary satellites clear to all of you? Okay, then let's move on to the next one. So having discussed the geostationary orbits already, the next one we have is the polar orbit. So you can see here in the picture itself that the orbit this time is going through the poles, isn't it? The one we saw before was going like this. So it was above the equator. Now it is above the poles. So we call them polar orbits. So an orbit in which the satellite passes above or nearly above both the poles of the Earth. Now, they are not at such a big height like the geostationary satellites. The ones we are talking specifically as per our specification is basically low polar orbits. So they don't go up above more than 2,000 kilometers. Okay. Now, the time period of such orbits is 2 hours. So you can see the before one, geostationary ones, it was 24 hours. But then this one takes only 2 hours to go around the Earth once. So that tells you that these are moving much faster. Then they are used mainly for weather forecasting, observation of the Earth, taking pictures, the Google pictures that you see on the Google Maps, military spying. Okay. Now, how they are able to do this is, so once when they move, so they are moving around the Earth once. Okay. By the time they move once and come back to where they have started, because it comes back in 2 hours, Earth would have slightly moved. Earth would have slightly rotated in its axis. So it would be coming across a different position of the Earth. Then it will scan that position and then come back. When by the time it reaches back, Earth would have rotated again a bit more. Like that, in a short span of time, it can basically cover the whole of the Earth. That is why it is used for weather forecasting and observation of the Earth. So what are the main differences between geostationary and polar satellites? Geostationary satellites are moving around the Earth above the equator. They are moving from one pole of the Earth to the other. Geostationary satellites are at much higher height, 36,000 kilometers, whereas these polar orbits are only at a height of 2,000 kilometers. Geostationary satellites are taking 24 hours for one rotation, whereas polar orbits takes only 2 hours for one rotation. Geostationary satellites are used for communication and satellite communication, whereas polar orbits are used for weather forecasting, observation of the Earth, military spying, etc. Okay, so I hope you got the difference between the two types of orbits and the satellites. Okay, so we saw that there are two types of orbits which the artificial satellites moving around the Earth can take. We saw what are the properties or characteristics of each type of orbit and how one orbit is different from the other. But there is also a similarity between both the orbits. If you go back and look at the pictures, you can see it doesn't matter whether it is a geostationary orbit or it is a polar orbit. The path taken, the orbit's shape is circular. Now, how does that happen? So that happens, or to know why that happens, the first thing you need to identify there is what type of force is acting between the satellite and the planet. So think about a satellite moving around a planet. What is the force that acts between them? It is the gravitational force of attraction. And this gravitational force of attraction is always acting towards the center of the planet. It's always acting towards the center of the planet. And this force is always at right angles to the velocity of the satellite. So if I have a planet here and if I have a satellite, the satellite is trying to go like this. But this force of attraction between the satellite and the planet keeps pulling it towards the planet. Okay, so it is acting towards the center and at the end it will take a circular path. You don't need to know too much details about it. So the main thing you need to know is you need to identify which force acts between the planet and the satellite. That is a gravitational force. What is the direction of that force? It is always acting towards the center of the planet. How does it make the circular orbit? How does it make the orbit circular? It is because this force is always acting at 90 degrees to the velocity. And it's not just in this case. Generally, if an object is moving and you have a force acting perpendicular to that object, then you can make that object move in a circular path. Okay, so the key things you need to take away is the force acting between the satellite and the planet is a gravitational force, and then it always acts towards the center of the planet, and this force is acting at right angles to the velocity. Okay, it's not done. Now, another question they can ask you is, how is it possible that something that is going in a circle goes at a constant speed, but it is accelerating? Okay, so I have something that is moving clockwise like this. I'm saying it is always going at a speed of 30 meters per second. How is it possible that it is accelerating? Because acceleration is not depending on speed. What is acceleration depending on? Acceleration is depending on velocity. So at this point, if I look, it is moving, the velocity is always at a tangent. So it is moving towards the right at 30 meters per second. If I look at this point, it is moving down at 30 meters per second. If I look at this point, it is moving towards the left at 30 meters per second. And if I look at this point, it is moving up at 30 meters per second. Okay, so whenever an object is moving in a circle, the direction of the object at a particular position is given by a tangent to that position. That is the first thing. So at any position I look, I need to, if I'm talking about A, B, C, and D, at any position, the direction of the object at that position is given by a tangent. So I've shown you the tangents at A, B, C, and D. You can see that everywhere the direction is different, isn't it? So whenever the direction is different, even though speed is the same, if the direction is different, what changes? The velocity changes. Why is the velocity changing? Because the direction is changing. And if velocity changes, the object accelerates. So if they ask you for, say, 2 marks, how is it possible that the object is accelerating even when the speed is not changing? Your answer should be yes, speed is not changing, but velocity is changing because direction is changing, and acceleration depends on velocity. So is that part clear, all of you? These orbits are circular because the gravitational force that is acting on the object is always acting towards the center of the planet, and it is at 90 degrees to the velocity, which makes it move in a circular orbit. Then how is it possible that something that is moving in a circular orbit is moving at a constant speed but still has an acceleration? It is possible because acceleration doesn't depend on speed. Acceleration depends on velocity. Here, the velocity is changing because the direction of the object keeps on changing, and hence the object accelerates. Okay? So the last thing that we are going to see here is how is the speed of a planet related to its distance from a sun. Same thing is applicable for satellites from a planet also. So when the planets are in stable orbit means they are at a particular height, and at that particular height they have the right speed. If the height changes, then automatically they have to readjust the speed or the other way around. Okay, so for every height there is a particular speed. Now when we talk about planets and sun, the planets that are much closer to the sun, due to the less distance between them, they have a very strong force of attraction. And if they don't overcome that strong force of attraction, what will happen? They will go and crash into the sun. So to avoid that, they move much faster. So the planets that are much closer to the sun, they move faster compared to the planets that are away from the sun. And why do they do that? Because they have a strong force of attraction. Now, let's think about a planet like that, which is much closer to the sun. Say something happened and the speed of the planet decreased. What will happen? There is still that strong force of attraction between the planet and the sun. So if the speed of the planet decreases, automatically the sun will be able to pull the planet towards it, and the planet will accelerate towards the sun and go and crash. We don't want that to happen, do we? To avoid that, the planet should increase the distance between the planet and the sun. So what will happen? Whenever the speed of any object that is orbiting decreases. So whenever the speed is decreasing, what should they do automatically? Whenever the speed is decreasing, if the speed decreases, they should increase the distance. On the other hand, think about a planet that is much further away from the sun. So the force of attraction, the gravitational force of attraction between them is much small, isn't it? So when they have such smaller force of attraction, they will be moving also very slowly. But if all of a sudden such a planet speeds up, what will happen? If they speed up, they can overcome the force of attraction between the planet and the sun, because there's not much force of attraction between them. So they will then fly off. To avoid that, they will be moving closer to the sun. So how can we summarize what I have said here? So generally what you see is closer planets. If the planets are closer, they will have high speed. Okay, so since they have high speed, they already have high speed. So for such planets, if the speed decreases, what will happen? The gravitational force will become dominant. The gravitational force becomes dominant, and then there's a possibility that the planet will crash to the sun. So if the speed is decreasing, then automatically they should readjust their height, or they should readjust their distance. I think distance is a better word. So if speed decreases, then distance would increase. Okay, because they are already having a high speed, then when the speed will decrease, they have to automatically increase the distance so that there is still a balance. But if we are talking about planets that are further away from the sun, they already have a slow speed. In their case, what will happen if the speed increases, they can overcome the force of attraction. So they need to increase the force of attraction. So they have to come closer. So for them, the distance should decrease. Okay, this is how the planets or the orbiting objects would readjust depending on what happens to their speed. If their speed decreases, then their distance would increase. If their speed increases, then their distance would decrease. All of this is done just to balance the gravitational force of attraction between them. Okay, so I hope this is clear. Any doubts? Ask your teachers, which can be me also, once you're back in the lesson. Okay, then? I hope everything is clear. And otherwise, as I said, please do ask. Okay, then. Bye-bye.